Let's look at the next topics in section 2.7 on one-to-one functions in the horizontal line test and also graphing inverse functions. We've just learned how to find an inverse using the switch and solve strategy. So let's take this example of the basic quadratic function f of x equals x squared. We'll replace f of x with y. We switch and solve, and when we solve for y, when we take the square root of each side, don't forget the square root property. Notice when you take the square root of each side of an equation, there are two roots, the positive and negative. So here, for one x value, we're getting two y values. So remember, that's not a function, and this would not be an inverse, right? So remember, if we have a function f, one x value has to map to one y value. And remember, when we switch x and y between the inverse and its original function, well, that relationship now says that, well, a y value should map to one x value. Now, you're going to see this language discussing one-to-one functions, and that's where no two ordered pairs have the same second point. So what you really have there is a unique x value maps to one unique y value. And so that language one-to-one is very important. And what you'll find is that only one-to-one functions will have an inverse function and pass the horizontal line test. Now let's look at the horizontal line test. F will have an inverse function if a horizontal line does not intersect its graph more than once. So this is very, very similar to the vertical line test we saw, which was a test for a function. Remember, the vertical line test says that a vertical line can only intersect a graph once for it to be a function. And what that really captures is, for one x value, it will map to one y value. So when we reverse this with the inverse function, well, one y should only map to one x value. And that will be captured by the horizontal line. Let's look at a couple quick examples. So here, I have the example I showed you algebraically up here, where y equals x squared, our quadratic function. And we showed algebraically it is a function, but it does not have an inverse function. We went through the switch and solve strategy. So we already know the answer. Again, as a function, one x maps to one y on its graph. But notice that if I draw the horizontal line across the graph, we get two intersection points. So it fails the horizontal line test. Notice, for one particular y value, we're getting two x values. That will not be an inverse function. So this fails the horizontal line test. Now, here's our cubic function, y equals x cubed. Notice when I draw a horizontal line, I only get one intersection point. So this function does have an inverse. And notice the cubic function also would pass the vertical line test. The cubic function is what we would call the one-to-one function. So at the end, right, this fails the horizontal line test. So no inverse. This passes the horizontal line test and does have an inverse, which is actually one of the common functions we've studied, that its inverse would be the cube root. Now do pencil problem 3 for a quick exercise. Now let's looking at graphing inverse functions. So a function and its inverse have that relationship where the x and y values get switched. Now, on page 319 of your textbook, you'll see this topic introduced. And if you have a point on the graph of f, a, b, well, notice if we just switch the x and y values, that's going to be the point on the inverse function. And the graphs of a function and its inverse are reflections around the line y equals x due to this switching of the x and y values. And so when you're graphing a function and its inverse, if you do it correctly, you can always visually look and see if you have this symmetry or reflection around the line y equals x. Now, how to graph an inverse function? Well, if you have the points for f, you pretty much have the points for the inverse. Just switch x and y and then plot those points, you'll have the inverse function. In example 6 on page 320, we'll show you how you can graph the inverse of a function, knowing the points of f of x. So we have these points off a graph for f of x. So to find the points of the inverse, right, we're just going to switch x and y. So now I just create the table of coordinates of the inverse function. This would be -2, -3, 0, -1, and 2, 4. So all you have to do is just switch the x and y coordinates of the points for f of x, and you'll have the points for the inverse. So now I'm going to graph f of x and its inverse on the same graph. So I'll graph the first set of points for f of x. So here we have -3, -2, -1, 0, and then the point 4, 2. So this segment will look something like that. Now, let's graph the points for the inverse function. So now we have -2, -3, 0, -1, and then 2, 4. So this is the inverse function. This is the original function. And again, you will have this symmetry along the line y equals x. So again, you can see how the functions are mirror reflections of each other around that line. That's how you can verify you've graphed the function, its inverse, correctly. Now do pencil problem 4 for extra practice. The last topic in section 2.7 is finding the inverse of domain-restricted functions. So let's look at example 7 from the textbook on page 320. And we're given a function, x squared minus 1. Now, if you remember from our transformations, this is really the quadratic function shifted down 1 unit. So it'll look basically like this. With this point here, the vertex is here at -1. Now, if we apply the horizontal line test, notice it will fail. We have 2 intersection points. We don't have an inverse. So how do we create an inverse out of this function? Well, what we can do is restrict the domain. So if I undo these drawings here, here's what we can do. If we remove half of the function like that, now notice it will pass the horizontal line test. And so this is where the terminology domain-restricted functions comes from. If we restrict the domain of the function to x greater than or equal to 0, which you'll see in the problem, now essentially half the graph is taken away, it will pass the horizontal line test, and we can find an inverse function. Now we can solve for the inverse algebraically, but I'm also going to show you how to do it graphically as well. So let's apply our switch and solve strategy. Y equals x squared minus 1, and we do have to include the domain restriction. Now, switch x and y, and even in the domain restriction, x greater than or equal to 0 becomes y greater than or equal to 0. Now we need to solve for y here. So we'll get y squared equals x plus 1, y greater than or equal to 0. And then when we solve for y, we get y equals plus or minus square root of x plus 1, and we still have y greater than or equal to 0. Now at this point, initially, when you look at the plus minus, you would say we do not have a function. For one x value, we get 2 y values. However, because y is restricted to the greater than or equal to 0, the negative root will not apply. And thus, this is really your inverse function due to that domain restriction. Now, how can we graph this? Well, remember in the previous example, if we had the coordinate points for f, we would just switch x and y, and then we have the coordinate points for the inverse function. That's what we can do here. We just have to keep in mind whatever this domain restriction is when we come up with the table of coordinates for f of x. To find the points for f of x, we can choose x values to substitute into the function so long as we obey this domain restriction. Now remember, when we did transformations for the x squared function, we would start with x values starting at -2 going to +2. But because of the domain restriction, I can't use any negative values. I'm going to start at 0. And then substitute in this equation, x squared minus 1, that would be -1. And then x is 1, this would be 0, 2, 4 minus 1 is 3, x is 3, 9 minus 1 is 8, and when x is 4, this would be 16 minus 1, or 15. So as long as we obey that domain restriction, we can still come up with a table of coordinates. And now we just switch x and y. And now we have the points for our inverse function. So now we have -1, 0, 0, 1, 3, 2, 8, 3, and 15, 4. Now that we have the coordinate points, we can graph each set of table of coordinates. And I've done this here on this graph. Here's our graph of f of x, which is x squared minus 1. Here's our graph of the inverse function, which is square root of x plus 1. And so you'll see the coordinate points for each graph. Notice again that they have that symmetry, or look like mirror reflections of each other, around the line y equals x. And one last connection, we did solve for the inverse function, which was square root of x plus 1. Notice that's the square root function with a horizontal shift to the left of 1 unit. So notice normally the square root function starts here at 0, 0, and it has been shifted to the left 1 unit, as we would expect.